Welcome to the next video on our sinusoidal function unit. This focus today is to solve a variety of problems involving sinusoidal functions. The ones I'm giving you today have the equations already developed for you. It's just making sure you can apply the information that we have. It's really bringing all the information together that we've done so far. So for this function, we're going to identify the key characteristics from the equation. So we should know that the very first thing in front of the sign, that's our amplitude. So this has an amplitude of 15. The period we get by taking that k value, which is 3, and dividing 360 by it. So that gives us a period of 120. The phase shift comes from this, and remember it's opposite signs. So this is 60 units to the right. And then the last part gives us the equation of the axis of the curve, which is our vertical translation. So this is a vertical translation of up 17, but it makes the axis of the curve be at 17. Now what we're going to do with this is we're going to graph the curve and choose an appropriate scale. So let's talk briefly about max and min values, because that kind of tells us what we need to make our y values as. To get our max, we always take our axis of the curve, so axis, I'm just going to put axis and not axis of the curve, and then we would add the amplitude to it, and that will always give you your max. So in this case we have our 17, and if we add 15 to it, we're going to get 32 out of that. So we need to make sure that our y-axis goes as high as 32, and our min would be our axis minus the amplitude, so axis minus amp, and that's going to give us 17 take away 15, which is a 2. Now I think I've set this grid up so that if we were to make every block on the y-axis be worth 2, we're going to be able to get 32 blocks on here, or a scale of 32. So 2, 4, 6, 8, 10 would go here. 2, 4, 6, 8, 20 will go here. Whoops. Undo. There we go, undo. There we go. So this should be a 20, I believe. 2, 4, 6, 8, 10. So that's going to be 20. 2, 4, 6, 8. This will be 30. And that gives us our 32 happening here. All right, and this is our 0 line. Now, if we look at period, we need to make sure we make the x-axis, or in this case the t-axis, be able to work well for us. Now, if I take the period of 120 and divide that into 4 equal spots, that's going to give me 30. So if I were to make every 2 blocks, let's say, worth 30, that would be 30, 60, 90, 120. I should be able to get one cycle within that, one full cycle. And then 1, 2, 3, 4. That would take us up to 120, and 120 is 240. And then, whoops, 1, 2, 3, 4. That will take us to 360 here. So I should be able to span this by 3 cycles if I need to here. All right, to graph this, I know the axis of the curve has to be at 17, so I'm just going to kind of dot in where that axis will be, halfway between my 16 and 18 mark. So that's y equals 17 right there. And I'm going to ignore my phase shift for a moment. I know that sine has the y-intercept on the axis of the curve, and then it lands at the end of its cycle on the axis of the curve, and halfway in between the start and the finish of one cycle, I should be also on the axis of the curve. And then halfway between the first 2 pair of points, I should be at the maximum. So I should have a maximum here at 32 when x is 30, and I should have a min when x is 90. So those 5 dots would outline one cycle of that sine curve without the phase shift. Now what I'm going to do is take each one of those blue points and move them 60 degrees to the right, and 60 degrees is equivalent to, let me outline 60 degrees here, is equivalent to 4 blocks here. 1, 2, 3, 4, yep, 4 blocks. So I'm going to move each one of those over 4 blocks, which would be moving it 60 degrees to the right. 1, 2, 3, 4. Oh, that first one slid over and landed on the next anchor point there, and likewise 1, 2, 3, 4, that one's going to slide over, and similarly I would have 1, 2, 3, 4, my final anchor point here for that curve. sliding that one over. I've got to slide my maximum over 1, 2, 3, 4 blocks, which is 60 degrees. That slides over. And the minimum 1, 2, 3, 4, it's slid over 60 degrees. So my horizontal shift, that phase shift, horizontal translation, creates my curve. Let's try that one. Boop-a-doop-a-doo. Trying to draw this in without too much difficulty. There we go. So there's one cycle. And then I can just extend that back 4 blocks. 1, 2, 3, 4. I should be down at the, 2 blocks. I should be down at the min. And 2 blocks before that, I should be back on the axis of the curve. So continuing my curve on should look like that. And I can continue to do that in to complete a few more cycles of this curve. So basically every 2 blocks I'm putting in a new anchor point. And I just slid my picture again. I'm very good at doing that sometimes when I'm least expecting it. I don't know if you can hear any music in the background, but it's kind of distracting me a little bit. I think I moved that one over too much. That was supposed to be there. I'm in my office at home. Yeah, and right underneath the office is our basement, and in the basement we have a piano, and I don't know if you can hear it. Oh, it stopped. But yeah, it's a little bit distracting for me. There we go. Okay, so there's some cycles to that. Hopefully that makes sense. We're going to answer some questions that go with that. This graph is representing the height of a person during a Ferris wheel, where h is the height in meters and t is the time in seconds since the tracking has began. At what height did the person get on the Ferris wheel? Now, this does not mean the y-intercept in this case. What happens is that Ferris wheel, it gets people off and new people get on the cart, and then they turn it a bit, and then the next people get off that ride and new people come on, and so they spend a bit of time filling up the Ferris wheel and emptying it and filling it up. So this doesn't actually get tracked until that Ferris wheel gets going at a constant speed. So really assume that the person gets in at the lowest point, and that means they're going to get on at that 2 meter mark at the minimum value. The radius of our wheel should equal the amplitude, because if we think about what we have in terms of the axis, think of the axis as the middle of the wheel. The distance up to the top would have to be the same from the middle down to the bottom. So your amplitude really is the radius of the wheel. So the amplitude is 15, the radius of the wheel will be 15. The axis of the curve happens where the equation of the axis of the curve is. So the axis of the curve is y equals 17. That would represent the height of the axle of our wheel. So the middle point or the rotation point of that wheel or that circle is 17 meters above the ground. It's the height of the axle of the wheel or the middle point. The period is 120. Now that's the time for one, or the horizontal distance of one cycle, meaning really one cycle of the wheel is really one rotation of the wheel. So that 120 is matching up with the time. It's the time it takes for the wheel to make one complete revolution. All right, so I'm going to summarize that on the next page. But before we do that, I want to talk about part E and F. At what height is the person 3 seconds in to the ride? Since the tracking has begun. So this is 30 seconds down here at the bottom. 3 seconds is going to be super close to the y-axis here. If you look at this, it looks like 10, 12, 14. It looks like it's going to be somewhere between 14 and 15. Probably no lower than 14, but definitely lower than 16. So it's somewhere between 14 and 16, I think. And then what time is the person at a height of 30 meters? So I'm just going to outline where 30 meters is on our height. So 30 meters is up here. You can see, oh, there we are. I've got a spot right here. I could follow that down and see where that is. So that's somewhere just a bit more than 75. And then it happens again over here somewhere. If I track that down, it's probably somewhere close to 105. But we're going to solve that algebraically. So keep those two numbers in mind. Okay, so on this page, I've just summarized my explanations that I had for these parts A through D while we were talking about the graph. And then for part E, at what height is the person 3 seconds since the height has been tracked? So the 3 seconds, that's the time. It's the t is equal to 3. And at what height? We're trying to solve for height here. So h is equal to question mark. So I'm just subbing 3 in for the t, and I'm going to put that in the calculator. And we're going to solve that. So you'll notice that I have replaced the t here with a 3. Okay, so when I entered that in, I got that the height of that person is 14.6 meters, 3 seconds into the ride here. Okay, and now we're going to look at this question on the side here. What time, so we're solving for times, is the person, just trying to get this to erase here. Let's see if I can do this better. What time is the person at a height of 30 meters over the first 2 revolutions since being tracked? So if we put 30 in for our height, we're going to put a 30 here in where the height goes, and we're going to have 15 sine of 3t minus 60 plus 17. And what we're going to do at this point is isolate for the t. We want to get t by itself. So I'm going to undo the plus 17 by subtracting 17 from both sides. So 30 take away 17 is 13. And then the 15 is multiplying the sine of the angle. The angle part, if you think of the sine of an angle, the angle part is that 3 and then times t minus 60. I'm going to divide by 15, and we get 0.86 repeating. And that's equal to the sine of this angle thing. And then we're going to undo the sine by second function sine. And I'm keeping all those digits in my calculator here. And I get approximately 60.07 here, but really close to 60. Now, that's equal to the 3t minus 60. Now, we have to reach back to last unit. And when we talked about last unit, we had the cast rule. And we came up with the one answer of 60 degrees. That's in the first quadrant, but we know there's a second answer. Sine is positive also in the second quadrant. To get that other answer, that angle going from the positive x over to that terminal arm, I'm going to do 180 degrees and minus the 60, and that's going to give us about 120. So we get a second answer here of 120 being equal to the 3t minus 60. Let me see if I can make that, oops, undo, I'm just trying to make that a little bit bigger so you can see that. So that should be a t minus 60 here. Okay, and then we're going to solve those for our t values. I'm going to divide both sides by 3. So I get a 20.02 roughly, and then, so 20.02 when I divide that side by 3, and that's equal to t minus 60. I'm going to add 60 to both sides, and I get 80. So t is equal to 80, which makes sense because we said that was a little bit more than 75. And I'm going to solve the other one here. Divide 120 by 3. Oops, 120 divided by 3 is 40. We get 40 being equal to t minus 60. And then we're going to add 60 to both sides. And I get 100, and t equals 100, which again makes sense because we said it looked like it was just a little bit under the 105-second mark. So those are our 2 times over the first revolution since being tracked. The next thing I would do is add the period. The period's 120, so I'm going to add 120 for the next cycle. That means 120 plus 80 is 200 seconds, and if I take 100 and add 120 to it, I also get 220 seconds. So the 4 times over the first 2 revolutions since being tracked that it reaches the height of 30 would be at 80 seconds, 100 seconds, 200 seconds, and 220 seconds. Okay, so I've added in a therefore statement that matches, and of course you could take those to minutes and seconds if you would rather. But I've just left them in their second form. Hopefully that is making sense.